Okay guys, welcome to this vodcast where we're going to finish off our introduction to volumes of solids of revolution, and then we're going to backtrack a little bit and look at some CAS applications towards integration. Okay, let's begin where we left class last time, and that's with this particular question. We've got a region sandwiched between two curves, in this case a straight line y equals 2x and a basic parabola y equals x squared, and we're rotating it around the x-axis, carving out a solid in 3D space. Okay, so what do I need to do first? If you were thinking about finding the points of interception, then you're dead right. Okay, so quite a simple process, as you know. We set the two rules equal to each other, and we see that it intersects at x equals 0 and x equals 2. And in fact, if I'm rotating it about the x-axis, that's all I need. If I was rotating it about the y-axis, I'd need the corresponding y coordinate of those points of interception. I'll be looking at that shortly. Okay, so I need to set up my integral expression. So the volume will be pi, don't forget the pi, times over the interval 0 to 2, lower bound 0, upper bound 2, and you've got the upper function, which in this case is our linear rule, f of x. So let me just grab my pen. It's this function is your upper, and we're integrating in this direction, f of x, which is 2x, and I square it, so 2x all squared being 4x squared, minus my lower bound function, which is x squared. I square that, making it x to the power of 4. That's the line you see over here. Okay, then it's the usual process for anti-deriving, and voila, the end result is a value that captures the volume of the solid that I carve out by that rotation. What sort of a rotation? Let's just get a visual of it. So it's a region that would look like this. Not a region. A region is more two-dimensional understanding. It's a solid that I get look like that. If you can, yes. Hopefully you've got a bit of an imagination. You can see what I'm trying to draw, and you've got a shape that's carved out like that. Okay, let's now examine. Let me just get rid of this pen. Let's now examine what would be the volume if I take that same region sandwiched between the two curves and rotate it around the y-axis. Okay, when we take that region and rotate it around the y-axis, I need to think about upper bound function and lower bound function as oriented onto the positive y-axis. So I'm thinking about integrating it. Let me just grab my pen in this manner. Okay, so you can see in this particular case, the upper function is the squared function and the lower bound function is the linear graph. Okay, so I now need to think about expressing x in terms of y. So of course my linear rule has the basic form x is equal to y divided by 2, and my curved form has the my curved equation has the form y equals plus or minus the square root of y. Now, of course, in this particular case, the positive square root refers to that arm of the graph, and the negative root refers to that arm of the graph. So I'm really only interested in this particular rule, y equals the square root of x for the upper function, and x equals the square root of y for the upper function, and x equals y and 2 for the lower function. All right, so we're ready to perform our calculus magic and determine the volume that we get by rotating it around the y-axis. We begin by setting up our rule. Volume equals pi, and I'm integrating it, of course, from 0 to 4. 0 to 4. I take my upper rule, squared, and I subtract from it the lower rule, squared, and I'm integrating dy. Okay, let's just clean that up a little bit. 4, 0, y minus y minus y squared on 4 dy. Okay, this is looking good. Okay, so let's go through the process. So we've got 0 is equal to pi y squared on 2 minus y cubed on 12 for 0. We can take out 1/12 if we wish. Let's take out 1/12 if we wish. That's equal to pi on 12. So that becomes 6y squared minus y cubed for 0, leading to pi on 12. 4, that's 16 times 6. 16 times 6 is 96 minus 64 minus 0, 0. So, okay, so we're left with, what's that? That's 32 pi on 12, or 16, actually, sorry, there's 4 into both. So let's just get rid of that, or 8 pi on 3 is our final answer. I hope you had success as well. Okay guys, here's another one. More practice is more good. Okay, a solid is formed when the region bound by the x-axis in the graph of y equals 3 sine 2x between x equals 0 and x equals pi on 2 is rotated around the x-axis. Find the volume of this solid. Okay, this is not an area sandwiched between two curves. It's an area bounded by a curve in the x-axis, so it's nice and simple. So straight away, it's basically pi 0 to pi on 2, that rule squared, and it's just, this question is all about testing your skills in anti-deriving, the sort of skills we learnt back in chapter 7. So have a go, pause it now, have a go, and then come back and see if you've got the right answer. Okay, the first thing is, as always, you should draw a sketch to see the sort of region you're talking about. Of course, sine 2x is a function of period pi, and so from half the cycle would look like that. It's been dilated by a factor of 3 from the x-axis, so that's the region we're talking about, and we're going to be rotating that around the x-axis to create something like an egg shape at the end of the day. Okay, so what do? We set up our integral expression. We pi, don't forget the pi is the multiple 0 to pi on 2. We square our function, move any constants outside, and what are we doing over there? That's right, we're applying the double angle rule for cos as referenced to sine squared. So of course we're customizing that rule for 2x to 4x rather than x to 2x, and we're left with that integral to solve. Take the half outside of the integral, simplify the workspace, and then it's just routine from there, isn't it? X, and then of course you've got minus 1/4 sine 4x, etc., etc. Sub in the values and come up with your final answer. And there is the volume obtained by taking that curve that you see before you and swinging it around the x-axis. Remember, the units would be cubed units. Okay, here's another one. It's linking back to some of the skills you learnt back in exercise 8A when you're looking at the area. So firstly, draw the sketch of the basic log, the natural log function. You need to think about the region being described between the x-axis, the y-axis, and the line y equals 2. To see if you can determine what the area of that region will be. Sorry, no, it doesn't say that at all. Sketch the region and then appreciate what you need to do is calculate the volume of solid if that region is rotated about the y-axis. Have a go and we'll come back, when you're ready, come back to the answer. Okay, you're back from having a go and you would have drawn a region like that. Of course, I'm really not interested. Of course, well, y is equal to 2 when x is equal to e squared. So let me just mark that point here. But it's not really relevant, is it? Okay, because I'm integrating towards the y. So it's all about what? It's about making x the subject. So x is equal to e to the y, integrating it from 0 to 2. But of course, you're taking the rule and you're squaring it. So let's go through the process of this. So first things first, there it is, e to the y. I set up my integral volume equals pi 0 to 2 of my rule squared. ey becomes e to the 2y. I antiderive it, and it leads to that as your final expression. Not a big deal, is it? Okay, I hope you're getting success with this. Okay, here's a lovely little question that'll make you think a little bit, maybe a little bit more. What we're doing is taking that shaded region, the region bounded by the graph y squared is equal to 3x, so the sideways parabola, and the circle centered at the origin of radius 2. So we're taking that region and we're rotating it. How? We're rotating it around the x-axis. You need to find the volume of that solid. Have a think about how that might be done, rotating it around the x-axis. In fact, it's a little bit easier rotating it around the y-axis, but we're rotating it around the x-axis. Okay, so have a think and then come back and we'll go over the solution to it, but have a go yourselves. Okay, you're back. You're wanting to know how to proceed with this question. The first thing is find the coordinates of the point of intersection that you see before you. And this is done quite simply, isn't it? Because you've got both involve y squared is the perfect square. So these are the two rules we're going to equate. Out goes y squared and in comes 3x in its place. So let's have a look at that. Let me just get rid of the pen. Let's have a look at that. Oops, I've actually jumped the gun. I wish that came in earlier. Ignore that for now if you wish. Okay, so out goes y squared, as I said, and in comes 3x. We solve that. Clearly, it's a quadratic, leading to two potential solutions. You've got x equals 1 or x equals -4. Now, x equals -4 is not a feasible solution in this particular case, so we reject that and we stick with x equals 1. Okay, all right, so clearly when this point here, let me just grab my pen here, this must be the point 1, comma, okay, root 3. I don't really need the y component because I am integrating towards the x-axis. Now have a think about how this might occur. So it's not a region sandwiched between two curves that I'm rotating around the x-axis because both of those regions are bounded by the x-axis itself. So this is what I need to do. I need to split it up as two separate volumes of solid of revolution, spin each of those separate regions around the x-axis and calculate their volumes individually, V1 and V2, and then sum them together to get the volumes of solids. So hopefully you're seeing this as a separate case, is not the same thing as rotating an area sandwiched between two curves around one axis or the other, but rather both curves being bound by the x-axis. I have to separate it into two separate areas that I rotate individually around the x-axis. I might just make the point that, of course, if I was rotating around the y, it would be a difference of two curves. Upper curve being the circle, so I'd make x squared the subject, x squared the subject is 4 minus y squared, and x squared, well, x the subject over here, x is equal to y squared on 3, and it'd be a case of upper minus lower squared, so the integral would be something of the form volume is pi 0 to root 3, upper being 4 minus y squared, lower being y squared on 3 squared dy. So that's what I would be if I was rotating it around the y-axis. But I'm not, okay? I'm rotating around the x, so I split it up in those two separate volumes, V1 and V2. Let's proceed. So we're rotating around the x-axis, equation set up nicely for substitution because we've got y squareds involved. It's actually quite neat to be able to do it. So V1 is obtained by taking that curve y squared minus 3 from 0 to 1. So if I was to make y the subject, so this might throw some students. So y is obviously the positive square root of 3x because it's not plus or minus, it's only part of the curve that we're looking at. And if I square it, of course, I get back to 3x. So that's one way to think about it. So there's the volume. I'm integrating with respect to x from 0 to 1, leading to a volume of 3 pi on 2 units cubed for V1. V2 is integrating from 1 to 2 for my circle rule. Okay, so making y squared the subject, it leads quite nicely to 4 minus root x. So again, you might think of that as making y the subject plus or minus 4 minus x squared, and then you're squaring the rule, but you get back to where we started from. So it's actually nicely set up for substitution without having to mess with our formulas too much at all. Integrating that from 1 to 2 leads us to hang on, I've got to get rid of the pen, leads us to that expression. We sub it in, we get 5 pi on 3. We sum the two volumes separately together. Oops, and there you can see it, 3 pi on 2 plus 5 pi on 3 is 19 pi on 6. Okay, this is the last volume of solid question we're going to look at before we move on to the sort of skills that we saw in 8C. And this is a nice little question. Okay, let's have a think about it. The region defined by the inequalities, y greater than that parabola, y squared minus 2x plus 4, and y less than 4 is rotated about the line y equals 4. OMG. We're not talking about rotating around the x-axis or the y-axis. We're talking about a line parallel with the x-axis, y equals 4. Interesting. How do you think we go about this? First things first, we should sketch it. So guys, if you want to go off and have a go at this problem yourselves, please do so. If you're not sure how to proceed with this question, let's have a look. So let's have a sketch. Okay, well there's the tip. When asked to rotate a 2D region about a line parallel with one of the axes, translate as appropriate. So this question reduces to a rotation about the relevant axis. So if we're rotating it around the line y equals 4, in other words, we take our rule, translate it downwards by 4 units, so that what we're doing is taking a region and rotating around the x-axis, which would be equivalent to the question being asked. So here it is. So there's our rule, there's our parabola, there's the line y equals 4, and in fact that's clearly the rule, y equals x minus 1 squared plus 3. So you can see it's got a turning point at 1, 3. Not that that's relevant necessarily. Well, it's not in this particular case, but understand what we're doing with this question. So this might cause, we're not asking you to determine this area and rotate it around the x-axis, or taking that region and rotate it around the y-axis. What we're doing is asking you to take this region and rotate it around the line y equals 4. So let me get our rubber and get rid of all of that stuff. Okay, and what we're going to do is perform that translation. Okay, so we're going to move it down 4 units so it becomes exactly the same region. And now what we're going to do is perform, and you can see what we've done. We've just subtracted 4 from the rule to make it y equals x squared minus 2. So the rule has undergone that transformation. If it was a shift to left, in order to rotate it around the y, we replace x with x plus 2, for instance. You guys should be very familiar with the transformations, and then we go through the usual process. Volume is pi. We're rotating it from 0 to 2. Our rule is x squared minus 2x all squared dx, and that should lead to the right problems. Now, don't forget perfect square expansions. There's three terms to anti-differentiate. Let me just in case you don't. So of course that becomes x to the 4 minus 4x cubed plus 4x squared dx. That's what I'm anti-deriving. All right, and that should lead to the correct volume. So hopefully you're happy rotators of areas around the x or the y, or in fact any line parallel with one of the two axes. Okay, that's it for now. Let's move on to 8C. Okay, folks, here we are. We've backtracked to 8C, integration using a CAS calculator. Look, word of warning, it's a little bit of a quirky exercise, this one. It's kind of on the fringes of the course. It poses some interesting mathematics, but certainly some quirky mathematics. Do your best to follow along. It's not super important, and come and see me if you've got any questions about it. Okay, have a look at this one. Use a CAS calculator to evaluate that. All right, now, of course, you guys know where the integration feature is in your CAS calculator. No need for me to go over it. It's well and truly discovered. Not much to explain here. Remember, if it says evaluate to 3 decimal places, it's always code to pick up your CAS calculator and have a go. How about using your CAS in this particular instance? So you've got to find, here's your graph. It's e to the sine x minus 2. Interesting looking graph. Obviously, the power oscillates between values of -1 and +1, and the graph is shifted down by 2. Okay, so you have to find the area bounded by the curve and the x-axis between pi on 2 and 3 pi on 2. So this is one approach, is to firstly determine from what is the value of a, integrate from pi on 2 up to that a, and then plus the negative of the integral from a to 3 pi on 2. Have a look what I've got. I've actually not appropriately set my my interval on which to look for a solution. Let me just grab that pen. You can see there, I should have really had a lower bound of pi on 2 to 3 pi on 2. So it's led to a potential, well, a solution that's not relevant. It's obviously a value for x that lies outside of my interest. So it's a value lower than pi on 2, which is about 3.14 divided by 2. It's clearly not in the domain I'm interested in. So I choose the correct, let me just get rid of this pen. I choose the correct one, okay, there's just a comment about the restriction. And of course, anytime you're solving an expression or an equation set to 0 involving a trig function, you must always impose that restriction. Otherwise, you'll get a quirky answer. My imposed restriction wasn't strict enough. Nevertheless, I should be able to work out what is the value of a in this particular case. There's my value greater than pi on 2, greater than 1.5, less than 3 pi on 2. Okay, then I can set up my integrals. Okay, so, and I have to, actually it doesn't say, interestingly, it doesn't say to 3 decimal places, but that's what the answer here is providing. Now, in fact, there is no exact answer. Even if you set your calculator to the right setting, there is no exact answer. It can only approximate. It's a numerical approximation for a solution. Now, hopefully some of you in the crowd will be looking at that and thinking, why bother even find a? What about that old technique of setting the modulus of the function and just simply taking the integrating over the interval pi on 2 to 3 pi on 2? And of course, surely that would give you exactly the same answer, and indeed it does. So you can see before you, without even needing to worry about where it's crossing the x-axis over the required interval of x, the use of the mod gets you there. So if you've got use of a calculator, why on earth wouldn't you perform that little trick? Okay, so a big part of 8C is these net signed area functions. So have a look at this. It's probably something you've never seen before. You've got some function defined as the antiderivative of 1 to x. So x is the unknown of the integrand. Now the integrand, let me just grab a pen. The integrand is this. It's with respect, it's using a dummy variable. It's using some variable, not x, in order to express it. It wouldn't make sense to work with x because x becomes the upper bound, the upper terminal in this integral function. But have a think about what this is creating. So let's just click on this. Okay, that's obviously 1 on x. And what we're interested in is a function that as x is growing, in other words, as x is growing in the positive direction from 1, so obviously that's the point 1, comma 1. Okay, as x is growing greater than 1, it's sweeping through a bigger and bigger area. So x is going to sweep through a bigger and bigger area as x is growing. So this is an increasing function for values of x bigger than 1. The larger x is, the greater the value of the function is, but you see it's going to grow at a smaller and smaller rate. So as x moves in the positive direction, we're actually only increasing the function by the value of the function by smaller and smaller amounts. Okay, now let's just have a think about this. So there it is. So um, I've got, oh, actually, hang on. So we've got, if I was to replace x by, so in here, I've got an up, what I'm doing is determining the area from x equals 1 to x equals 4.02. It's about 1.1, it's about 1.419. Well, what is that value, and why is it that it's going to be approximately equal to the natural log of that x value of 4.029? Why do you think that is? What's going on here? Okay, so there it is. If we were to think of the function f of x defined in this way, on a restriction that x is greater than 1, what we've got is part of the log graph. So let me just grab a pen here. Let's make sense of this. So if I was to anti-derive 1 on t over an interval 1 to x, where x is the upper bound. So here's our definition for x, 1 on t dt. Remember, you have to use a variable other than x in this setup. What we have is the natural log of t. Now I don't need to put a mod around that because x is greater than 1. Okay, from x to 1, leading to the natural log of x minus the natural log of 1. Natural log of 1 is 0, leading to the natural log function. Okay, so that's the curve you see before you. It's a part of the natural log function. All right, this, in fact, what we could do, in fact, and just to appreciate where we're at, therefore, here is our 1 on x, 1 on t function. We're starting at 1, 1. There's x. There's a value of 1, x equals 1, and as x is growing larger in this direction, this area becomes equivalent to, there's our upper bound x, becomes natural log of x. So it's describing an area function, a net signed area function. All right, what happens if we were to allow values of x not just greater than 1, but greater than 0? What would the graph look like? Let's have a think about it. So for x is proper fractions, in other words, positive proper fractions. So let's have a think. So suppose x we allowed to be equal to a quarter. Okay, so our f of x will be equal to 1/4 to 1, 1 on t dt. Now, because a quarter is less than 1, we're expecting a negative value. We've got natural log of t 1/4 to 1, and we sub in 1/4 minus natural log of 1, which as we know is 0, and that's equivalent to minus natural log of 4, a negative value. And you can see as x approaches 0 from the positive side, as x gets smaller and smaller and smaller, a quarter, a tenth, a hundredth, etc., etc., f of x will get larger in the negative direction, will approach negative infinity. Okay, in other words, the graph, our net signed area graph, will start to resemble the full natural log graph. Okay, is that making sense? So if I'm integrating from 1 to x, okay, from x to 1, I get an increasingly large area, but from 1 to x, if I reverse the terminals, I get a negative area. So it's all matching up nicely as well. All right, talk about quirky little questions so that you might enjoy this one. Use a CAS calculator to find an approximate value of the definite integral 0 to pi on 3 of cos x squared dx. And to plot the graph of f of x equals 0 to x using dummy variable. Remember, if I've got a net signed area function, some initial value to the open-ended upper bound, it has to be a variable other than x. So t is the go-to. So we're talking about x taking on any value from minus pi and 4 to pi. Now, of course, this value can be obtained directly from your CAS, no big deal. But let's have a play with this net signed area function and see what we come up with. Okay, so the value of this definite integral becomes the value of the area function under the cos x squared graph from 0 to pi on 3. Okay, so that's what f of pi on 3 represents, the area under the cos x squared graph from 0 to pi on 3. All right, so if we're asked to actually get the calculator to redefine it, it can't. And the reason being is there is no natural description. So the area function can't be simplified to something nice and neat. So it keeps that, definite integral expression. Now, when we do graph it, we set that particular rule into our graphing screen. We get a function like that, an interesting looking function. And if we type in x equals pi on 3, which as you can see there is approximately 1.047, so that would be pi on 3. We sub it into, we can use our gsolve and ycalc to determine the approximate y value, and you've got 0.9281 it looks like, or 6181 I think. Okay, and that would be equivalent to just that value is what you should get when you just whack that into your CAS directly. So it's working out, it's a net signed area graph, and it's telling you the net signed area when x hits pi on 3 under the curve y equals x squared. Let's analyze this a little bit more to see if we can make more sense of this. Okay, there is the net signed area curve from 0 to various values. We typed in a value just above 1, which resulted in pi on 3, and we had a y value of 0.9281, something like that. What's going on here? Why is it that our function is dropping? So you can see here it's continuing to pick up speed. It hits some particular value of x, and then it starts to decrease. What do you think is representing that decrease? Hits another x value over here and starts to increase to a point, and then does a decrease yet again. How is that related to our cos x squared graph, or a cos t squared graph, and the understanding that we're talking about a net signed area function. What would account for that drop in our net signed area? So if you were thinking something along the lines of, well, it must be where the graph is dipping below the x-axis, then you'd be dead right. So here's what I've done is just done a y-calc situation. So clearly when x, I've just whacked in a value, x equals 2.4786, and I've got a y value of 0.58. But what's going on here? Let's have a think about it. Okay, so I've now got the CAS to just sketch y equals cos x squared from minus pi on 4 to positive pi. And you can see, therefore, what's going on. See if you can find the connections between the two graphs. So at this point here would equate to this point over here on our net signed area graph. So the graph is making positive gains as x is getting larger and larger from 0. We're sweeping out a larger area under the cos x squared curve. It hits that particular value of x, and then it starts to contribute negative area, hence the dip. Okay, hence the dip. It drops at the greatest rate at some point, and then a smaller and smaller amount of negative areas contributed until it hits this point over here. Let's just call it A and B, related to A over here and B over there. Okay, now we return to a positive signed area until we hit that 2.4786, 2.4876, and in fact the area that I've swept out, the net signed area, so that's here, let's call that point C, is I've got the calculator on the left. Let me just get rid of some of this stuff. So you can see the calculator is got the net signed area. It's swept through from x equals 0 to 2.4786, 2.4786, and it's got this area indicated over here, 0.57, and that's simply the value of the function at x equals c. So there it is over here, the value of the net signed area function. But you can see the key points. So again, A occurs here. It then the net signed area function starts to dip to account for the inclusion of a negative area. The net signed area drops. We then pick up again after B until we hit that point C. And if we were to keep going, it would continue to gain some area, albeit less rapidly. It hits that point D, where it then starts to drop off again, and so on and so forth. So there's the connection between the two. All right, I've got a further question for you interested punters out there. You can see for negative values of x, over here, remember from x is 0 up to minus pi on 4, you can see that the cos squared graph is above the x-axis. Therefore, why does it drop away in the negative direction over here? What's causing our net signed area function to be negative for values of x between minus pi on 4 and 4, when you can see clearly, hang on, let me just get rid of this, when clearly the function, the cos squared function is positive, is in the top half of the graph. I wonder if you can see what's going on there. Let me just make it clear. Here's our original function. So just to make it clear, let's get rid of that. So why is our net signed area function negative for negative values of x between minus pi and 4 when the cos squared function is clearly not negative, is above the x-axis over there? Well, you can see, hopefully, those of you on the ball, when x is negative, what we're doing is integrating from 0 to a value lower than it. And so what the integral is doing is making that, therefore, a negative value. So even though this is positive, because we're integrating, say, from 0 to what's the value, less than minus pi on 8, say, okay, cos x squared dx, that'll of course be the same thing as negative 0 to minus pi on 8 cos x squared dx, which we know is a positive value. So this here is positive because the graph is positive, is above the x-axis, but because the terminals have been, we're going from a lower bound to an upper bound where the upper bound is lesser, it means it's interpreting as a negative value. Now, this is all analysis. It's unlikely you'd ever be tested on this truly, but it's interesting to explore these functions, these net signed area functions, but certainly do not get too concerned by them. They're right on the fringe of the course. Okay, so let's finish off with this particular example. The rule for the function is defined as an area function. Okay, we're defining it for any value of x, both positive and negative. So we'll think about the ramifications for that in a minute, which are quite interesting. All right, so let's go through the process of trying to get a neater definition of f of x. We should be able to do that because we can certainly antiderive sine t. We know the antiderivative is negative cos t. I'll just section out the negative. Upper bound x, lower bound 0. This is what f of x is equal to. Okay, which is equal to minus brackets cos x minus 1, which is in fact 1 minus cos x. Now cos x, which is a function that can take on any value from minus 1 to positive 1, clearly this is a function whose range is anything from 0 to 2. Now you might ask yourself, hang on, that's a bit curious, but let's have it explore and see why this makes sense. So as x is growing larger and larger and larger, clearly this point here is pi. As x is growing from 0 to pi, our area goes from, okay, so let's say f of pi will be 1 minus 1, which is 2, so it's reaching its maximum net signed area. And as x is growing larger, continues to grow larger, so there's obviously 3 pi on 2 minus 1, we're starting to bring in a negative area. So f of 3 pi on 2 will be equal to 1 minus cos 3 pi on 2, which as we know is equal to 0. We've got our area of 1. Okay, so here's an area of negative 1, here's an area of positive 1, and so on and so forth. So it'll continue to grow in that direction, making perfect sense. A net signed area function. Curious situation when x is less than 0. Okay, it's a curious situation. Does this rule still hold for the net signed area? Well, it does. It does and it doesn't. There's a bit of a limitation on understanding x is our upper bound. So let's think about it in the negative direction. So as we go over here at minus pi, surely would have an area of negative 2 is what our function should be saying. So f of minus pi, according to our rule, is 1 minus cos of minus pi, which is 1 minus 1, which is 2. Why is it positive 2 when clearly that sine area is below the curve? And it's exactly for the reason we've discussed before. If our upper bound is less than our lower bound, it'll be the negative opposite. So it's kind of effective as a net signed area function up to for positive values of x. For negative values of x, it's the opposite. So what we're doing is, of course, integrating from minus pi to 0 in this particular case, sine t, and getting the negative opposite of the integral minus pi to 0, sine t dt, which turns out to be negative of negative 2, which is positive 2. All right, so you get the idea, don't you? Okay, I think that's all good. All right, we'll leave it at that. I think we're good from there. Okay, good. See you for now, folks. I was going to do the length along a curve, but we'll save that for the next time I see you in class. Please make sure you listen to these podcasts and are up to date next time I see you, which will be next Friday. That'll be bye for now.